Yeah, we're live. I'm just doing some admin here and then we'll get on this. I need to add a community link. Community link in the description so that people can join our Discord and generate new link. Copy. Yeah. I don't know why. I don't know why I posted. That's that. That should be a. Anyways, I have no idea why that became that. Okay, cool. So over the past sorry, over the past few weeks, we've worked on this audio application. We have this audio application that basically works on this board. Just as a refresher, it works on this NRF 52840DK dongle, the one that I'm using right now. And what this does right now, what the code on this does right now, it's the code. The link to the code is in the description. There's a GitHub repository already. What this code does right now is it has an audio. How do I call it? An audio thread. It has many threads, but right now we're working on the audio thread. It has an audio thread, and this audio thread basically just sits there. When this audio thread is activated, it just sits there and basically senses audio. What we want to do now is a continuation of the last audio stream, where we built an audio filter. I think it was. We can go rebuild it again. Actually, let me see. Can I open this new window? Can I open that? Can I? Yeah, no, that goes to the wrong screen. So let's go here. Let's build a new. Let's go here. Let's build a new window. Let me see. Let me see. Let's build a new window here. I'm confused. What was I doing? T filter. T filter. T filter. T filter design. Yeah, T filter engineer. Yes. Okay. Cool. So yeah, the last time we were on this, we designed a filter. We designed an audio filter, and I have it somewhere on my notes. It's on paper. We designed a filter that was stop. We did a stop band of. Let's actually just design the filter again. Let's design the filter, and then we carry it over to our code, and then we start using it so that we can do it. Basically, we want to filter our audio and basically sense for claps. And the way we decided to do that is we added a stop band for just background audio, so 0 to 1500. So this is basically, we're making a bandpass filter. And then I think the gain we said for this one was 0 gain, and I think the ripple was -40. That's fine, that should work. That's a stop band. Okay, cool. And then we wanted to add a pass band, and our pass band goes from 2000 hertz, 2 kilohertz, 2000 hertz to it goes to 6000 hertz. You can technically you can leave this to go all the way to the ceiling, to go all the way to the top, which by Nyquist theorem is 22,000 kilohertz, because we are sampling at 44,100 kilohertz. But that's okay, that's not for today. And then the gain, we did it at 1, I think. And then the ripple, we did it at 0.5 decibels, so 0.5 decibels. Cool. And we designed the filter by pressing a button. They're overlapping bands. Why are the bands overlapping? Okay, cool. Thank you so much. This is cool. Normally you do this in math, or I think Bartholomew. Are you here, Bartholomew? Bartholomew does this in MATLAB. I know. I think so, yeah. So if Bartholomew is here and is in the comments, he would do this in MATLAB, so that would be cool. Nah, Okay, again, I'm rushing. So let's do 2000 there. Let's design the filter. What? They are overlapping bands. Yes, Bartholomew would do this in MATLAB. So cool. But I'm a pleb. I'm just a human. I'm not an electronic engineer. So I do this. I use. I'm confused. Why is this not working? Remove the passband and add it again. Okay, add a passband, and then the passband should start from 2000, and then it should end at 6000, and then the gain would be 1, and the ripple would be 0.5. 0.5. Design filter. The overlapping bands. Oh, I see the problem. So this is 2000, this is 6000, and then this is 1 and that 0.5, and our sampling frequency is 44,100. And the desired taps, we actually did the desired taps. Let's leave it at minimum, see how many it gives us. What's happening? Okay. Start afresh. Always works. 44,100. Cool. And then 0 to we want to kill 0 to 1,500. I think that was what we did last time, if you follow the video. And then the gain here was 0. And then the ripple, we put it at whoa. This is not cool. So, just give me a few moments. Let me settle in. Let's add a sample frequency, 44,100. And then we said, I think I will set my desired taps for 50. And then this is I want to add this separately. So let's add a stop band, which is 0 to 1,500. And then in this one, I will set the gain to be 0, the ripple to be -40. Cool. And then I want to add a pass band, which will go from 2000 hertz, and it will go all the way to 6000 hertz. And then I want a gain of 1, and then I want a ripple of 0.5. 0.5. Okay, cool. And then the tops is 50, blah, 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 blah. We got it. We got a filter. I'm very curious if I do minimum design filter. That's strange. It takes a little while longer. Maybe there's some math. Maybe it has to go through very many simulations. Yeah, let's wait. I think it might have to go through quite a lot of simulations before it gives us one. Yeah, that didn't work out. That did not work out. Is this an actual filter? Whoa. That doesn't seem like an actual filter, but it does. This looks. Bartholomew, why doesn't this work? Why am I getting a non-truncated coefficient? Why is this going all the way to infinity? Do you know? Okay, anyways, I don't want to use 237 taps because that's too much. So let's just set it to 50. I thought the software would be better than me, but let's just use our normal filter. So, but that's cool. We have our gain versus frequency, and then we have our thing that ends at. This is not cool. Why is it not ending at 0? Why is it not ending at 0? This is not cool. But anyways, cool. That's fine. So let's use that. Let's see. Those are all good. So 0 to 1,500, 0 gain, 40 ripples, 2,000 to 6,000, 1 gain, 0.5 ripple. Yeah, cool. This is fine. This also works. So now let's actually go get this source code and then put it in our code. What we actually need, this is also how to apply it, but we are going to be using Kimsys DSP. Kimsys DSP. We're going to be using this. Yeah, I wanna see if I can get to the math part, basic math function. So we're going to be using Kimsys DSP, and I assume we're going to have an FIR filter. There should be an FIR implementation somewhere. I did see it earlier. No, not that. Yeah, let's even look at that filter example, and then we can copy. Where's the documentation for this? So FIR init and FIR 32. Yeah, so this is the two functions we're going to use. And the software kind of, it's like the website has updated since I used it a lot, because it used to be white and stuff. So we need to initialize this, and then we need to use FIR 32 like this to apply the filter, and then there's some code that Bartholomew already did, which is here. It's going to be Zephyr custom Zephyr BLE. It's going to be here. There's a branch by Bartholomew. There's a pull request by Bartholomew that adds a hysteretic detector. Adds a hysteretic detector to our code. So this is going to be, once we filter the thing out, once we filter out all the stuff that we don't want, we're now going to use this hysteretic detector to chunk down. And what am I trying to explain here? We're going to use this hysteretic detector so that we don't detect a clap more than once. Once we detect a clap, we stay on that clap level for enough time so that we don't we only get one sample of that filter. Hysteresis is a system that depends on history. So if it was up, don't detect it as up again. Don't detect the threshold crossing again. Although this one that just passes a raw RMS value. What we are going to do, since we are now using Kimsys DSP, is we are going to filter out all the stuff that is not claps, all the stuff that does not fit in our passband. Remember here, yeah, all the stuff that does not fit in our passband, we're going to filter it out, and yes, filter out the stuff that does not fit in our passband. Yes, we remove that. We stay with our passband. Now our passband is going to have this this amount of information that we're going to use, and in that information we're going to now use a power analysis rather than the last code was using an RMS thing, which was just trying to get things working so that we can start applying things slowly. But rather right now we're going to use power, and that is in power. Is there power? Let's see. Power F32. Yeah, let's look at power. And this must be like stupidly small for people to see. So yeah, we are going to use this as a power detector and to compute a threshold rather than an RMS, basically. That's basically what we're going to do. most of the code that we're going to add today is going to be very little. We're probably going to add like 20 lines of code. I think more of the work is understanding what is happening than the code itself. So let's actually go copy this filter that we have into our code base. This is actually all I want. Copy. And this doesn't use, this uses double. That's fine. So that's okay. So as you Control E. Okay. Control R. Control E. Okay. Control Shift R. Control E. Shift R. Shift R. Control E. Is it okay, cool. Space A, Control E. Let's put that there, and then let's take audio H. Let's put it in there. Space A, Control E, so that we can jump in between these three quickly. So the first thing I want to do is actually define filter coefficients. Filter coefficients. So and then let's come out. Let's do that, and then let's do that. Let's remove them here. So and coefficients. Okay, and then I want to do Control V, and this is just all our coefficients. That's all. We call it filter tabs. So filter tabs it's the size of your impulse response, basically. I've explained this in different things, and I don't want to jump into a really theoretical thing again. Define num tabs, and then in here I will say num tabs is 50. I kind of want it to be online with the other things above, and then here I want to put in num tabs. Num tabs. Okay, cool. So what does that give us? Git diff. What am I on? What was I doing? What was I doing? What was I doing? What was I doing? Oh yeah, I was trying to look at the RMS float so that I could see what to do with it. Cool. And this is what happens when you move from codebase to codebase. Just so quickly. Git add audio. Git add source. Actually, let's use it first before we add it. So we've defined some filter coefficients here, and they exist now. And then we need to do a few more. We need to add a couple of things. So the thing is, we need to define another mem block. We need to define another mem block because we need a buffer. The FIR filter needs to maintain a buffer that lives for a little bit. So we need a buffer that is the same size as our float size, plus I think the filter coefficients, so that the FIR buffer can hold those things. Let me see. So let's, rather than do that, let's say filter definitions. So let's add a buffer in here. So define something like we should probably use a mem block, but I don't want to use a mem block right now because because of the odd sizing. Yes, I don't want to use a mem block right now because of the odd sizing. So I want to do something like define FIR buffer, and then this will be double FIR buffer. No. So something like I just need a normal like a normal float. And then this will be FIR FIR. I'm confused. I'm confused in naming this stuff, so I'll just keep it like that. And this FIR buffer will be block size, but block size is in bytes. Block size is in bytes, isn't it? Block size is in bytes, but I don't want it to be in byte. I want it to be samples per block. I don't want it to be in bytes because I want it to be in samples per block plus tabs, and then this needs to exist plus num tabs minus 1. Okay. I'm gonna pause for questions just now so that I can see. It's just a double. It's just a double, isn't it? It's just a double. It's just a double. That's all I need. So it's just a float, isn't it? Isn't it? Let's see where we're using floats again. It's just a float. Yeah, it's fine. Just leave it as a float like that. I'm posing for questions just right now. Let's see. Any questions? No questions. Cool. I think that means what I'm doing is very confusing or very clear. That's what it means. I think it's very confusing. I don't know. I don't understand these things really quickly that easily. So we have number of tabs. We have an FIR buffer, and then let's just call it FIR state. Then it's easier to remember what this thing is. So I just want to build all the definitions so that when I get to applying this Kims's functions, it's super straightforward. Okay, cool. So we've got our filter tabs, we've got our filter state, we've got our number of tabs. So right now, let's now go here into audio service and start actually processing this thing. Here, rather than do the float into that and then do this and that, I don't want to compute the RMS signals. I no longer want to compute the RMS. Okay, cool. So I no longer want to compute the RMS because I'm no longer using that. So let's remove that code. And then let's do that. Let's do that. It's you. Yeah, let's do that. Let's do that. That's fine. Remove that as well. Okay. So now let's actually do some stuff. Let's actually do apply FIR filters. So let's put some code in here and then apply FIR. Apply FIR. Or let's call it FIR work. Once it works, we can remove all these comments, but before that, let's just label these places so that we know that this is where we're working in, and FIR. Okay, so the first thing we need to do is, now that we have our code data, we need to normalize it, which is a problem that I think I didn't do. So this actually, sorry about this. I'm trying to remember what was here and how I did it. What I'm trying to determine right now is how to take this whole block and normalize it all at once, rather than normalizing each of the, because see here, now we've hit our first problem of the stream. See here, FIR filter. This takes a source of float 32s. Convert int 32t buffer to float. See. If anyone knows how to do this quickly, let me know as well. Yeah. I want to convert a whole buffer. Is that actually true? Will it implicitly do it for me? This is a problem. This is a problem because we are embedded and we don't have that much space already when we build this. Already when we build this, we're already kind of running out of RAM. NRF 52840 dongle, and then NRF 52840 the So there's that, and then we want to build for that, and then we want it to be pristine, and then we want it always. Does anyone have an idea of how to do it for the whole block at once? That's the problem. So I don't want to make another. Look, we're already making two intermediate buffers. We already make an FIR state buffer. I'm not so sure. Yeah, that's fine. That's fine. I'm not so sure that I want to add another additional buffer, because we're already at like something like 60% of the RAM. And if we just keep eating RAM like that, we're probably going to end up finishing it like that. So there's probably some sort of zero copy implementation that lets us do this on a block scale, basically. And that's what I'm trying to find. That's what I'm trying to look for. How to convert all of this, instead of getting the block and walking through the block and making it. So think about it this way. Our audio receiver is still on in the background. It's still sensing audio. And we're sensing audio in batches of 100 milliseconds. The longer it takes to process this audio, the more it will cost us. So the first thing we can actually do, we can actually go very naive. It's fine. We can actually do very naive. We can actually go very naive and do an interpolation and do a conversion. We can go naively and then we can optimize this later. Let's try that. But as you can see, we're already using 40% of RAM. So I have a feeling if we add another buffer right now, it will just, okay, you know what, let's just do it and then we'll see where it ends up. So we're already using 40%. I would want to not do that. I just wanted to do that. I want to do it once. So where's the division? I want to see the divider. I don't want to just do a cast. I feel like a cast is going to lose data, but might not be. Okay. I can just cast it. I kind of know how to do this. I think you can go through, you can do this division. Let's just do that, yeah. Let's just do that. And then let's make a buffer. Let's make a buffer the same size as you see here. So yeah, we can use it here and we can clear it, and eventually we will find a way. I'm sure there's a way I can hand this over to, I can do this in a block scale, but I don't know yet. I'm sure there's a way I can do this in a block scale. So let's do that. Are this normalized? Yeah, normalize samples. Something like that. So let's do float. Let's go from here. Float samples f. It's going to be it's a block size actually. because we're reading in 32 bits. It's a block size, and then yeah, there's something that I'm not connecting, but it's fine, so it's fine. And then for int b equals 0, b less than block size, b class plus, let's do that. And then for each of these, let's do this. Let's just fill in this buffer. Yeah, this is what I wanted to do. Let's do it naively, and then we come back and do it. We come back and see if we can actually make it much better. So here I would do samples f, samples f b, index b is equals to float of samples I for int. I already used b. Float int f. Okay, let's do it f. I already used v. No one told me I already used v, so it's fine. I'm pretty sure there's something I'm missing. Sample f. Actually, let's quickly do some very legal things here and see if they work, and then we'll come back to this. So in here, let's do that, and then log 1 and then here I just want to remove this because that we're not gonna actually, yeah. I don't need to double it here. Well, I need to double it to print it. So this is going to samples f. I have a feeling this is a seg fault or a hard fault for sure. This is a redeclaration, so that's gonna fail. And then let's do a build. Let's just do a build and see what happens. Any questions so far? Any questions right now? I have more questions than I think people who are watching me, because I'm a little confused. I need to do more research on how I can consume that whole thing as a block. There's something. I'm naive at something. There's something I'm missing. I know how I need to do it. I need to pass it all in as a block. And then once I have it as a block, I need to operate on it as a block, because that will be much easier. There's some little part I don't understand. Yeah, there's some part where my data structures is not going well. My data structure knowledge is not playing well somewhere there, because I should be able to operate on a whole buffer at once. But that only worked previously because we could give the buffer to, we could just give the 32-bit buffer into, it's a 32-bit, but it's a float, but it's an int 32. This is probably where you need something like SIMD. It would make sense if you could squeeze all of the conversions into like single instructions, multiple data, and then you could fill it out. That sort of is simply what that's not such a huge jump. Yeah, so let's actually do that. Let's run that code. What board do you need? You just need a normal USB cable. I need a normal USB cable. I just need a normal USB cable. This is a normal USB cable. Cool. So here, let's plug that in and see what happens. So first of all, we need to pack it. Don't try and remember stuff. Do not try and remember stuff because it's harder to remember stuff than to just do it. Let's go back here. We already have all of that data. NRF down. I'm looking for this command. I'm looking for this command. This command I'm looking for. I need command I'm looking for. This, let's call it pack.zip. Okay, should pack it with a big warning. Perfect. And then I need this command, and then I should be able to be, but this is gonna go to pack rather than Blinky. So let's do that. I've put the board in bootloader mode. Pushing code out to it, and then we should be able to jump on a screen session with that. On a screen, yeah, SCM0. SCM0. It works. So let's, if we connect to Bluetooth, it's going to start, trying to connect here to Bluetooth. If I connect to Bluetooth, it's going to start audio sensing. And once it starts audio sensing, it should show us the values, which is fine, which is cool, which is what we want to see. Connect to Bluetooth, fine. I'm gonna scan it. Okay, I'm connecting now. Yeah. We are normalizing. We are normalizing. We are good. We are normalizing. Okay. Yes. So our normalization is working. So this is working. So here we are normalizing and it works. And we do actually get samples. Amazing. So we normalize them. We get them. Now I want to go back and I want to do, what's the next thing I want to do? I want to, if I wrote some notes. I always write some notes and I'm always reading from my notes. So guychoose.com. I wrote some notes. I'm always reading from my notes. I write notes before the sessions and then I come back and I do them in the sessions later. So we already have defined that. We need to basically, we already have an FIR state, and then this is an instance. We need Ah, I see. Look, we need an output block. I feel like I want to use another mem block. But I don't really have to. I just want to. We need FIR state. We need another mem block for. I know what I'm gonna do. You see this? I'm gonna use this samples block twice. This is gonna be insane, so that's fine. Okay, cool. Let's make it as dirty as possible. And normalization. And then after this, we need to do apply filter. And filter apply. No, but that's gonna be our input block. That's gonna be our input block. We don't wanna do that. Damn. Float samples, filtered samples. I'm sorry, people. I've been writing very long for 2 days or something, and I forgot how to write C. So I don't remember how to do this here. And in all honesty, also at work, I've been really debugging a bunch of. I've been debugging a lot of. I have an issue. I have an issue on this FPGA, and I need to implement USB DFU upgrades on this FPGA. And so for the last like few days, I've not been doing C. I've more been doing this weird layer between C and RTL, and so I'm sort of like my head is more towards doing hardware design right now. But if I do this for a few hours, it will come back. But that's fine. That's okay. So this is the filtered samples. That's the output block, and the input block is going to be our thing from the other side. So let's do it here. Come on, why are you doing that? Why are you doing that? Num taps block size. I want to initialize it with coefficients, state, and block size. Yeah, let's just do that. Let's actually go to the DSP functions and then see for init. That's it. What does that do? I like that the Kimchi's documentation looks like. I bet you it's just Doxygen. I like that it looks like the Zephyr one. So in, out, num taps, da 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 da. Okay, cool. We know how to do this. Don't we know how to do this? We can sort of just call this function. Yeah. We can just sort of call this function. I can even copy it from here. So there's this. I will do that. Is that copy? And then let's apply our filter. Simply. I am sorry about that, or I can actually just do that. Something like that. So that it all fits within the 80. Okay, so what do you take first? What's the first thing you take? Instance. Yeah, I remember this. Oh, I just made one. You can just make one. You can just call it and make one. So let's make one here. ARM FIR init F32. That's it. Now we actually want an instance. Okay, and then we call this one FIR. Okay, cool. So that's that. There's that. We've gotten it. So and then we want to initialize it. We want num taps. We have num taps already defined. Okay, we have num taps. Float 32 filter coefficients. No, this is wonder where float 32T is coming from. Is float 32 coming from? Is float 32T coming from? Is this from Kimsey's? Yeah, this is from Kimsey's. Okay, cool. So float 32 is coming from Kimsey's. That's fine. So what do we want to do here? These are coefficients. We call them FIR. What did we call them? What did we call them? Filter tops. I want to call this filter tops. Let me just look at the documentation. That's just so we make sure we're doing the right thing, really, to be honest. Let's go back. Filter tops. So parameters, the instance, yes. Number of tops, num tops, number of coefficient tops, num tops, yes, that's fine. Points to the filter coefficient, yeah. Points to the buffer, yeah, that's fine. That is okay. Yeah, that's fine because it's already it's a list, so it's already that's fine. And then this points to the state buffer. We have a state buffer, so FIR state. Control E. FIR state. Okay. So this should fail, yeah. FIR state. We have a warning somewhere. I don't like the warning. Yeah, it's fine. Yeah, cool. So this one initializes that. I see what is happening. We are initializing the filter, the instance of that filter itself. Because when you do this, I can jump to other code that I've written, but I don't want to do that. I think it's going to be more confusing. But basically, no, let's go here. GitHub, Zach, this is, and then this is going to be LAN or something. Don't show what I'm working on. Don't show what I'm working on. It's gonna show all of my repos, so it's fine. You're gonna see the repo, but you don't know it exists, so it's fine. DSP. DSP. See this ones. So when you apply a filter, when you like convolve a filter, let me see, it's fine. So what did I come here to explain? You build a filter and then it sits there, it contains your coefficients, and then you can apply it to some incoming signal. Basically, that's it. So we build a filter here, and then we push it into this we make the destination array just the source array plus the response, impulse response. Well, that's really what we just did. We made an impulse response that becomes a thing. So yes, we haven't used that. That's okay. That's fine. We haven't used that. I put this in my notes somewhere. So we've instantiated it here. Cool. There's this. How is that? This I should fix that. FIR process. Input, output. Please just update the thing. Move slow and fix everything you find as you find it. And then in here, let's actually just fix this. Fix things as you find them. Fix things as you find them. So in here, this is going to be here. This is going to be here. There's some error here. This code, this is wrong. Yeah. So this is C. And then that C is here, because you're the one who's going to use this at work. This is a manual for you to use at work. So It's not for anyone. Git status, git add posts, 2025 online 10 git commit dash amend. That fixes it. Git push dash force. That's fine. That puts it up there. So in the meanwhile, while that is updating, we can see here, we can just call the function we actually are interested in is this one. So we pass in the FIR that we've instantiated, we pass in an input array and an output array, and then we see what happens. Perfect. ARM, FIR, init, no. F32, just F32, yeah. FIR F32, and then in here we want to pass in an FIR, and then after the FIR, and then here we want to pass in samples F, yeah. And then after samples F, we want to put output, and then we want to say filtered samples, yes. And then after that, we want to say block size, yeah. So, and then I just basically want to do this again. And then it's here. Okay, so instead of samples F, we want to go through filtered samples. Filtered samples. And we can use F again because we just did it now. So this doesn't need to be floatingized. This doesn't need to be floatingized at all. We can just walk through filtered samples, and then we can do log R filtered sample filtered sample that, and then F, and then let's put actually you don't need that. I'll remove that. Filtered sample that, and then F, and then actually you don't even need you, and then I can just put this here, and then I can say here, and then the first thing I need to pass in is F, and then the second thing I need to pass in is filtered samples, filtered Y, and then in filtered samples I need to pass in the value F. And that initially just basically gives us whatever we want, and this is a problem. Control E, implicit conversion, and then this wants to be a double. Does it work out? Does it sort of work out? I can put this on the next line so that it doesn't let's put this on the next line so it just shows nicely and someone can see what's happening. Okay, cool. I think that's our filter applied. I really genuinely believe so. If I detect, yeah, so that's the code. The code shows properly now. We don't need this open now. We can close this now. So that's closed. Sorry. Somehow I've messed up my state. That's fine. It's okay. Ghosty crashed. CD Zephyr project applications Zephyr custom, and then nvim Control Shift T, and then in here what are we gonna do? Clear. Control R. In here we're going to activate. Okay, and then we're gonna do west build dash p dash b and rf. Actually, Control R west build. Okay. I think that's really it. We did actually build an FIR filter. We applied it, and it's in there. There is a bit of cleaning up that we need to go and do to make sure that we're converting the data really right. That's not good. This is not good. This is not good. This doesn't bode well for us. This means something wrong. That means something went wrong, actually. I am using it. I am using it. Why does it think it's not used? Ah, I remember. We need a K config probably. We need a K config. Because do you remember we did this? Actually, we did this. I remember now. We need a K config for this. So this is here. We need a K config for Kimsys DSP. I don't know, FIR. I don't know. So let's go see such K config. Yeah. Does this make sense? Bartholomew, does this make sense? Anyone who's here? Does this make sense? Can anyone follow what is happening? So config Kimsys DSP and then something else. So here's going to be config Kimsys DSP. Okay. Let's go here. Finite. Is this in? What are you in? What section do you belong into? Let's close that. Filtering. Okay. Filter. Okay, that's it. Filtering. And because we're not using the statistics function right now, we can remove it. We're not using this. we're not using this because we were using this for the root mean square, so we can do filtering. And we'll probably need power as well. Power. Where's it? Where's power in? We will probably need power at some point. See this one. See when we this power functions. Where is the power one? Power. Power. Oh, we still need statistics as well. Config Kimsys DSP statistics. Yeah. Okay, that's fine. That should give us everything. Yeah, and that's okay. Let's do. It's fine. Anyways, this is going to be kind of the tail end of this session. We have built a filter. We have built a filter. We have applied a filter. It needs to be correct, but we have built and applied a filter. So let's see what happens. 613. Wow, why? This is not cool. Why is that not used? It's gonna crash for sure. Okay, that's fine. This is gonna crash. I don't know. Wait. I see. Yeah, it's fine. It's always. I don't see how this doesn't crash. Anyways, I don't see, and I don't see where we. So, anyways, let me just check. Tops coefficient state. Init. Yeah. This is gonna crash. I don't know why, but there's something I'm missing. So that the tops and the state are not used. But it did add filter, so I can see that filtering was added. So I don't know why. But let's see. Maybe it needs to compile top to them and then add the libraries and then realize it's using them, and then it's gonna be okay. Because they are used actually. If this doesn't work, I'm gonna stop there. Then I'm gonna go do some more research, and then we'll handle that tomorrow, I guess.
Are you done?
Almost.
We'll do it all.
Oh wait, it didn't crash. Okay. it. Okay, cool. Yeah, it's fine. I don't really care right now. Control R, DFU. I'll put the app in bootloader mode. Control Shift T while that is loading, so that I'm ready to run the screen command, and hopefully we can run it. Screen. That immediately crashes. That immediately crashes, which means these errors are actually significant. Okay, cool. So there's a reason this is named part 1. So there you go. We have built an FIR filter. We know we have some state where we're going to apply it to, and we have some samples where we're going to pull them from. So what we're going to do is take a pose from there from today, and I need to go and find out what is it that I'm doing wrong. This feels like a small kconfig thing, because the issue seems to be that it doesn't find them. The issue seems to be it doesn't find them. So what I'm going to do is I'm going to go and try and research what is it that I have not, what is it that I have included something, but I have not included everything I need to include for that to work. Once I have that figured out, then we can do another. Let's see, it's here somewhere. Merged, yeah, it's all there. There's no warnings. I see no warnings at all. Everything is in there. Yeah, but this is a problem. This is a problem. Filter type defines but not used. This is defined but also not used. That's okay. That's a problem. This is not working somehow. Working, but my notes tell me that should work. We have a yep. We have a yep. Yeah. ARM, FIR init, F32, FIR, that's fine. It's cool. Coefficients, that's fine, they're there. That's it, tapped. FIR state, it's there. Block size is there, that should work. And then whenever we get our DMA callback that we have filled it, we do FIR, F32, that. Them through the filter. Output, input, output, block size. Something is wrong. I'm missing something. Anyways, thank you so much for joining me today. That was cool. That was part 1 of implementing an FIR filter and applying it to our audio samples. Thank you so much for coming. Cheers. See you next time. We'll get it done.